So, part two. In the first part, we created the game, we laid the foundations, and in this part, we're going to be looking at the MiniMax algorithm. And we're going to see what the MiniMax algorithm is, how we implemented it with code. Remember, the series is all about purely .NET. And then lastly, just see if we can compete against it and if it actually works. Check it out. Looking at the definition of MiniMax algorithm on Wikipedia, we can see it's an AI algorithm, and the important part here is it's a minimizing the possible loss. And so basically, what we're saying is it will look at all the different options it has, and it will choose the one where it's got the least chance of loss. The opposite is maximum, and we'll touch on that as well if you want to do it differently. If you want to optimize for gains, but and the idea is also for you've got alternative players, and you switch between the maximizing player, which is you or the algorithm, and the minimizing player, which is the opponent. And ultimately, it's a brute force algorithm where we run through all the permutations, and we're assuming that the opponent will always choose their best move, and we will choose the least likely route for us to lose. And essentially, also when we've got the opportunity to win, it'll choose that. There's a nice little example over here where basically you're at this point. So it speaks about the maximizing player, which is yourself or the bot that you're busy with, the algorithm, and you want to choose the best possible outcome, and the opponent will always choose their best possible outcome. That's what we're assuming. Now, MiniMax will always try to reduce the minimizing the possible loss. So you'll see in this scenario, ultimately, if you go down the decision trees, if I go right, the decisions after that, and in the end, if I go right, the score that we come out with is -7. If I go left, the score that we come out is -10. And so we, as a maximizing player, will choose the minimum loss. So we'll choose that going forward. Getting a little bit more practical now with regards to TicTacToe. I think let's take a look at an example. So just from a conceptual point of view, we're the maximizing player, the MiniMax algorithm, and we will choose the best possible spot. So basically what that means is we've got a few options here. The first option is, let's say we are X. The first option is over here, second option is there, third option is there. So let's assume we play there, and the next one we play there, and the next one we play there. All right. So what happens now is we need to score each of the possible moves. So we go through all the decisions, we score them, and because we're the maximizing player now, we will then pick the best score. And so from just looking at it, you can already see this is the best score. We'll get the highest positive value. If we win the game, we get a positive score. If we lose the game, we'll get a negative score. And so basically what it means is this is definitely the choice. But to score, you actually need to look at the final state, because we don't know, will we win, will we lose? It's hard to say. Well, it's impossible to say unless we've gone through all the steps. And so what needs to happen now, for instance, in this one, is we say, did we win, did we lose, is it a draw? No, it's not. So then we need to take it a step further, and we say, all right, well, if let's just draw the X, we break it down a step further from there. just to say, okay, this breaks down into here. So if we chose to go there, this was our turn, or the maximizing player's turn. Now it becomes the minimizing player's turn. All right. And the minimizing player, the opponent, has two choices. They can go here or they can go here. And ultimately, this one, we lose. Now, if over on this one, this would end up in a draw. And if we were to score this, we would basically say that this is maybe 0, this is -1, and green is +1 if you win. And so what we basically have over here is, because it's the minimizing player's turn, -1 and 0, we have to choose the minimum score. So we end up choosing -1. We choose the least score. And over here, ultimately this will end up in a draw. I'm not going to paint and draw it all out. And so what we're saying is this is going to be a loss, a win, a draw. And we then, as a maximizing player on this level, we choose the maximum. So remember over here, we didn't choose the maximum because it's the other player's turn. We choose the minimum because that is the best that our opponent would do. And so we're basically saying, if we're going down this route, we are going to lose. And ultimately, then we make the decision and we will choose this spot to go for the win. Looking back at the pseudocode, just at understanding what that would look like in Tic-Tac-Toe, we basically look at, there's two options. If it's the maximizing player, then we basically want to choose the max score, which is the bot, the MiniMax bot. If it's the opponent, the minimizing player, we'll choose the min. And it's a recursive function. And basically we'll go one level lower, one level lower, one level lower, and until we hit a leaf node, or until it's a terminal node. Basically, until we win, lose, or draw the game. Only then can we score. So check if the game's done. If not, get the score, and if for the next move, and we go a level further. And so basically, there's also a depth that's important to note. So here, the depth decreases, or you could also say it increases depending on how you write it. But the depth changes. And the reason the depth is important is, if, for instance, you had a situation where you could, the opponent is going to win the very next move, or you calculate all the different options that you have and you realize, well, the opponent is going to win even if you block that direct move. In a few moves down the line, the opponent's anyway going to win. We could then end up saying, okay, well, just go anywhere. It doesn't really matter. We're going to lose. The equal probability of loss, which isn't quite accurate, or not how a human player would play. Even if we're going to lose, a human player would still avoid the very next loss, the closest loss. So basically what we're saying is, we'd prefer to lose later than lose immediately, and vice versa. If we can win right away, versus winning a few steps down the line, we always choose the win right away. Even if it's guaranteed that there's no stopping us, we will win the game later, we'll always choose immediate win. And that's why depth is important as well. But yeah, let's get into some code. So here we are. Let's just go to the MiniMax bot, and this is basically from, if you haven't seen the foundations of how we created the game, please check out the first video to understand how the game flow works. But basically it came down to, when you create a new bot, you just have to implement iPlayer, and this isn't needed. Type is just a type and a name. It really is just one move that you have to implement, the make move. And what we've done is we implementing the make move, and it's the game state that comes in. Remember, the game state is your board state, available positions, and all those items as we went through in the first video. So, right, so what this basically does now, thinking back on the algorithm, is because applying a move would alter the game. We don't want to actually alter the game when we're checking move 1, is it good? No, it's bad. Move 2. So we're going to clone the state. And it's a little bit more expensive from a resource point of view, because every permutation, we clone the board, try the different parts, and all of them we clone to go one level deeper, etc. But we don't want to alter the board and then revert the board, and so the board needs to stay the same. We're creating a copy, we're working out what's the best move, and then we'll apply the move. And so what happens is we've got all the available moves that we want to make, and we're basically just saying, get me the scores for all of them, and ultimately choose the best move. If the score that's come out is less than the best move, we just carry on and check the next move. Otherwise, we capture that move, and in the end, we have the best move to come out. And how this works is we go into the MiniMax, and remember, based on the Wikipedia, there's 2 parts. Three parts. The first is checking the game state, and that's what we do here. So we picked a move, we'll apply it to the state. This is the clone state. We'll check the result. Is it terminal? Is it a win, a loss, or a draw? If not, we need to go a level deeper, and what we basically then end up doing is we look at all the next available spots, and we end up going through those and doing that. And when we do the apply move, it actually changes the player's turn, which will mean it's the other player's turn. And we collect all the scores for this level, and basically this is the minimizing or maximizing player. Is it my turn? If it is, then I'll choose the max. If it's not, choose the minimum. That's the idea. And then the scoring, as I mentioned as well. If it's a draw, I've used the score 0. If it's a loss, I've used -10. If it's a win, 10. And the idea with the depth is I've gone for the incrementing depth. So every level I increase the counter. And basically what I'm saying, if we can win on the very first depth, that will be 9 points. Otherwise, second level 8 points, third level 7 points, etc. And we want to win earlier, so we'll always end up picking the shortest route to victory, if there is one, and we will always prevent the loss as far as possible as well. If we want to then play the game, as we saw in the first video, we've got 2 front ends, the command line and the web. Let's just jump to the command line, and as you'll remember, we can just pass in the plays we want. Let's keep the human player, and let's change random to MiniMax. As easy as that. Let's keep it like that. One thing I did remember from the first video is that because it plays multiple games, once the game is done, it didn't pause. So we will just do a console.readline over here, just to keep the game somewhat, so we can actually see somebody winning, if I remember correctly. So let's run that. Zoom in a little bit over here. There we go. And let's say I move to spot 3. So far so good. Let's block him. 1, 2, 3, 4, 5, 6, 7. We go to 7. And now we're in a little bit of trouble, because he's cornered us. Basically, if we go there, he's going to go there and win. If we go there, let's just try for the last one, number 9. And there we go, player one wins, so he beat us. So that's it from the MiniMax algorithm. You're welcome to have a look at the source code on GitHub. And once again as well, I've got the web version, and that is hosted on TicTacToe filteredcode.com. If you go over there, and you will see that we've got an extra bot there. And previously we just had random bot. Now if you choose MiniMax bot, you'll see there are the options there. So that the bot will play first. This time we'll play in this corner, play over here, and once again they've trapped us. So if we go there, he goes there and wins. If we go there, it goes there. So let's play here. There we go, we lose. And it's pretty hard to win, so it's impossible to win, but it's can at least invoke a draw. Let's see. There we go. It's the best we'll be able to do against this one. I'd like to also just have a little chat about the implementation side of things. I know it's not directly related to MiniMax, but there was a little bit of a spanner in the works, and I thought it was worth sharing. So the algorithm itself, from a AI perspective, I think is fairly straightforward. It maybe seems a little bit more complicated, and sometimes when you get it wrong, troubleshooting can be quite tedious. But conceptually, I mean, if you look at the Wikipedia, that code is even simpler than mine. It's fairly straightforward. As long as you've got your ways of copying the board and cloning the board, etc., and that works nicely. There are a few challenges with this, and the first one is this isn't machine learning. This is classified as AI, yes, but not machine learning. And the reason for that is we're not actually training a model. We're not learning and training a model and then loading a model and basing our predictions of that, or exploiting based on a learned model. We are basically running an algorithm that brute forces and makes the best decision. So technically classified as AI, but not machine learning. Now, why is that a problem? It is because of the decision I made to stick with Blazor. And what I mean with that is, once again, think of all the permutations you can get. Let's actually give it a Google to see how many, but I'm sure there's thousands of permutations that a game can end up with. Basically, we need to go through all of those. Let's actually have a quick Google. TicTacToe permutations. Sheesh, I'm not quite sure. That's quite possible. Maybe that is true. Yeah, I don't know. Can't trust everything on the web, but that's quite a lot. I didn't expect it to be that high. 255,000. I might just check afterwards, validate that. But basically, because we've got so many permutations, and we're running this on Blazor, which runs on the client, on the mobile, on the web. So what that means is we have to create a copy of the board, then run the permutations, then a copy of that board and run all the permutations, copy of that one, all the way until we get to the terminal node or the leaf node. And because of that, you can imagine how many objects we have to end up copying. And because I decided not to go and mutate the state, but copy the state and run off my copied state, mutate the copied state. And so Blazor runs with, we can at least run the MiniMax bot on the client side. That's great. You don't need a server side. But the problem is there's not proper support for multi-threading yet. And so the UI thread also seems to be responsible for the garbage collection. And so what happens is the more copies we have, it just gets too slow. And you end up clicking and you end up waiting for everything just is stuck for a while. And I mean, you can make it responsive with async await, but you still have no response from the bot for 45 seconds to sometimes even a minute, depending on which device you use, and that's not usable. So I've had to figure out a way around this. My assumption is this is only going to be the case for MiniMax or an algorithm that's not learned, and because it has to go through all these permutations. Once we've got a learned model, and we just have to predict based on a model, that will work just fine. So what have I done with Blazor to overcome that? I've basically taken, I've created a web version of the bot. Where did I create that? Over here. And what that ends up doing is it goes to the server. And I created a Azure function. And in that function, it basically, we take the game state, we serialize it, and with a bit more time, I would have done this better, possibly taking the objects properly. I've just taken the entire objects and serialized it, and doing a little bit of manual intervention on the other side with regards to the players. But the idea is we serialize the state, send it to the server, we create the MiniMax bot instance on the server, and there we've got proper performance. I mean, it's really quick then on that on the server side. So the Azure function, it's hosted as a function on a consumption base, and it's a consumption plan, so we only pay for what we use. I doubt many people will be playing on this game with Tic Tac Toe, so that's the idea there. We send the state over. On the other side, we deserialize it, and we make a decision and send the response back. Once the response comes back, we just pass it on and say, off you go. And a little bit of sugar to make it nice, that if the connection drops, you don't get some ugly error, but just a notification saying there's no connectivity, and it'll continue to retry until you've got connection established again. So that's the idea. And on the function side, it really is just one function. We read the body that comes in over here, and a little bit of hacking that I've done because I didn't break down the items properly and do proper serialization, deserialization. I've just taken the entire object, replaced the types with because we used a web MiniMax bot on this side, we want to use a MiniMax bot. And there's another little hack here. You can just read the comments here. I'm not going to go too deep into it, but the idea is then once we've got that set up, we would just basically call the make move, because it's the player's term will be the MiniMax bot. They'll return the move, and off it goes. And that seems to work quite nicely. And yeah, finally, once again, we've got the code. And with the code, I've created a workflow. This was there in the previous one. I've just added a separate YAML step to do the actual deployment to the function. And so we deploy the function part, and then on a separate step, the Blazor app. So yeah, that's that. And then on this end, just looking in Azure once again, it's a basic standard function app. There's nothing special about that. So there's only that one function that we run, and that we can then execute. It's a HTTP trigger, and that then helps us to just get our response back. So the next step is then to do the machine learning algorithms. I'll probably look at the Q-learning next, the reinforcement learning. That's one I've really been quite excited to do. And yeah, let's see how that works out. My intention is then to use the console app to train, and then host it on the Blazor application, and with the learned model possibly being served up from the server. And that should work seamlessly on the client's machine. Once you've got the model pulled down, you should be good to go. So yeah, let's see how that goes.